Nuclear fusion will disrupt industries. As Russia-Ukraine war rages on, we are hearing about the Zaporizhzhia Nuclear Power Plant standoff in Ukraine. Nuclear power plants are very valuable and dangerous to operate. In the race to harness nuclear fusion, USA, Russia, Europe, Japan are in the same team. Nuclear fission and nuclear fusion are two of the most promising options for new sources of energy. Both processes involve the release of massive amounts of energy from relatively small amounts of matter, making them much more efficient than traditional fossil fuel sources. But which one is better? Nuclear fission occurs when an atom is split into smaller atoms, releasing a large amount of energy in the process. This energy can be harnessed to generate electricity, which is why nuclear power plants use fission to produce power. Fusion, on the other hand, occurs when two atoms are combined to form a larger atom. This process also releases a huge amount of energy, which can be used to generate electricity or power other devices. So, which is better? In terms of efficiency, fusion wins hands down. Nuclear fusion reactions release about 4 times as much energy as nuclear fission reactions, making it a much more efficient source of power. In terms of safety, nuclear fission is more dangerous than fusion as it produces harmful weapons-grade radioactive waste in the fuel rods that need to be stored safely away for thousands of years. Viability of nuclear fusion. Nuclear fusion has the potential to be a clean and safe energy source, but it has yet to be proven viable on a commercial scale. The key to nuclear fusion is using heat and pressure to force atoms of hydrogen together to form atoms of helium. This process releases tremendous amounts of energy, which can be harnessed to generate electricity. There are 2 main types of nuclear fusion: magnetic confinement fusion, MCF, and inertial confinement fusion, ICF. MCF uses magnetic fields to confine and compress the hydrogen plasma, the hot, charged state of matter in which the atoms have been forced together. The most common type of MCF is tokamak. ICF uses powerful lasers or particle beams to heat and compress a small pellet of hydrogen fuel. The resulting explosion creates conditions that are conducive to nuclear fusion. Both MCF and ICF are difficult to achieve on a commercial scale, and there are still many technical challenges that need to be overcome. For example, the amount of energy required to ignite nuclear fusion is much greater than the amount of energy that is released by the reaction. In addition, the high temperatures and pressures required for nuclear fusion can lead to the formation of harmful byproducts, such as neutron radiation. Despite these challenges, many scientists believe that nuclear fusion is the best hope for humanity's long-term energy needs. Fusion reactors could provide a virtually limitless supply of clean energy. Different approaches to nuclear fusion. The potential of nuclear fusion to provide a nearly limitless supply of energy has long been recognized, and its development has been the subject of intense research for many years. However, despite significant progress, the technical challenges associated with achieving nuclear fusion remain formidable. In particular, the extremely high temperatures required for nuclear fusion make it difficult to confine the plasma, the gaseous state of a material composed of free electrons and atomic nuclei, in which fusion reactions take place. If these challenges can be overcome, nuclear fusion could have a transformative effect on the energy industry. Fusion power plants would be much smaller and more efficient than current nuclear fission plants, and they would produce no greenhouse gases or long-lived radioactive waste. As a result, nuclear fusion could play a key role in mitigating climate change and ensuring a sustainable energy future. There are many different approaches to nuclear fusion, but all involve using powerful magnetic fields to confine plasma in a small space. The most promising approach is inertial confinement fusion, ICF, in which laser beams or particle beams are used to heat and compress a tiny pellet of fuel, typically deuterium and tritium. This process triggers a rapid nuclear fusion reaction, which releases enormous amounts of energy. ICF has been extensively studied over the past few decades, and significant progress has been made in overcoming the technical challenges associated with it. In particular, recent advances in computer modeling and 3D printing have enabled the fabrication of increasingly complex ICF targets with greater precision. As a result, scientists are now confident that ICF can be used to generate electricity on a commercial scale. The first step toward realizing this goal is the construction of a prototype ICF power plant, known as an energy amplifier. Such a facility would use ICF to generate electricity with an efficiency of about 30%. This is significantly higher than the efficiency of current nuclear fission plants, which is around 10%. Moreover, an ICF power plant would be much smaller than a fission plant, making it easier and cheaper to build. If successful, an energy amplifier would pave the way for the construction of commercial ICF power plants. These plants would have an efficiency of approximately 60%, meaning that they would produce twice as much electricity as current fission plants while emitting no greenhouse gases or long-lived radioactive waste. The development of commercial ICF power plants would be a major undertaking, but the potential rewards are enormous. Nuclear fusion could provide humanity with a nearly limitless supply of clean energy, helping to mitigate climate change and ensure a sustainable energy future. How nuclear fusion would disrupt industries. The transportation sector would be one of the biggest beneficiaries of nuclear fusion. Electric cars would become the norm, as they would be cheaper to operate and maintain than gasoline-powered vehicles. Public transportation systems would also switch to electric power, dramatically reducing pollution and saving billions of dollars in fuel costs. The manufacturing industry would also benefit from nuclear fusion. The high temperatures required for fusion can be used to create new materials with unique properties. For example, fusion could be used to create super-strong metals or heat-resistant ceramics. These materials could be used in everything from airplanes to spacecraft. Nuclear fusion would also have a profound impact on the way we generate electricity. Current power plants rely on steam turbines to generate electricity. Fusion power plants would use magnetic fields to contain and control the superhot plasma created by the fusion process. This would be far more efficient than current methods, and could provide electricity for millions of homes and businesses. The potential applications of nuclear fusion are virtually limitless. It is an exciting technology that has the potential to change the world as we know it. How nuclear fusion would affect the energy market. The energy market is highly complex, with a large number of factors influencing price and demand. One of the most significant potential disruptors to the status quo is nuclear fusion. If commercialized, nuclear fusion could provide an almost limitless supply of safe, clean, and affordable energy. This would be a game changer for the energy market, as well as for the world at large. Fusion power plants would produce no greenhouse gas emissions, and would have minimal environmental impact. They would also be much cheaper to operate than current nuclear fission plants. Fusion could help to solve many of the world's energy problems. It could provide an abundant, safe, and environmentally friendly source of energy that would help to address concerns about climate change, energy security, and air pollution. ITER, International Thermonuclear Experimental Reactor. Nuclear fusion is the process by which two lighter atomic nuclei combine to form a heavier nucleus. In doing so, they release a tremendous amount of energy. This energy is what powers the sun and other stars. The fusion of two hydrogen atoms into a single helium atom is the simplest possible nuclear reaction. It is also the one that powers the sun. The sun's core temperatures are estimated to be around 15 million Kelvin. At these temperatures, the hydrogen atoms are moving so fast that they occasionally collide and fuse together. The resulting helium atom is slightly lighter than the sum of the two original hydrogen atoms. The difference in mass is converted into energy, according to Einstein's famous equation, E equals mc squared. This energy is released in the form of heat and light. The Sun's core is so hot that the hydrogen atoms are constantly undergoing fusion. In fact, it is estimated that each second, millions of hydrogen atoms are converted into helium atoms in the Sun's core. The Sun has been shining for about 4.6 billion years, and it will continue to shine for billions of years more because there is an almost limitless supply of hydrogen fuel. The same process that powers the Sun can be used to generate electricity on Earth. However, achieving the high temperatures necessary for nuclear fusion is difficult. Scientists have been working on this problem for many years, and there has been significant progress in recent years. In order to achieve nuclear fusion on Earth, scientists must heat a plasma, a gas of electrically charged particles, to extremely high temperatures. The most promising approach involves using magnetic fields to confine and control the plasma. There are several experimental devices called tokamaks that are designed to do just this. The largest and most advanced tokamak in operation today is called ITER, the International Thermonuclear Experimental Reactor. ITER is being built in France by an international consortium of 35 countries. When completed, it will weigh 23,000 tons and be as big as a cathedral. ITER will use a 500 megawatt MW microwave system to heat its plasma to 150 million degrees Celsius, 7 times hotter than the center of the Sun. At these temperatures, the hydrogen atoms will undergo fusion and release huge amounts of energy. ITER is scheduled to begin operation in 2025. If successful, ITER will prove that nuclear fusion can be used to generate electricity on a commercial scale. This would be a major breakthrough. Nuclear fusion could provide humanity with a virtually limitless source of clean, safe energy. The ITER Nuclear Fusion Research Agency is an international organization based in France that is responsible for the development and operation of the ITER fusion reactor. The name ITER is derived from the Latin word for the way, and the mission of the organization is to demonstrate the feasibility of fusion power as a renewable energy source. The ITER project was conceived in 1985 by representatives from Europe, the Soviet Union, Japan, and the United States. Construction of the ITER facility began in 2007, and it is expected to be fully operational by 2025. The ITER reactor will use a tokamak design to confine and heat plasma to temperatures in excess of 100 million degrees Celsius. This will allow the hydrogen atoms in the plasma to fuse together, releasing massive amounts of energy. The ITER facility will also be used to conduct scientific research into the potential of fusion power. This research will help scientists understand the challenges that need to be overcome before fusion power can be used on a commercial scale. The ITER organization is composed of 7 members: China, the European Union, India, Japan, Russia, South Korea, and the United States. Each member country has contributed money and resources to the construction of the ITER facility and the research that will be conducted there. The ITER facility is located in Catarac, France. When completed, it will be the largest international science project in history. Companies working on nuclear fusion. There are many companies working on nuclear fusion projects around the world. Here are some of the leading ones. General Fusion. This Canadian company is developing a novel approach to nuclear fusion called magnetized target fusion. This involves using a magnetized plasma target to compress and heat fusion fuel, triggering a nuclear reaction. The company has raised over $200 million in funding so far and is backed by Bill Gates, Jeff Bezos, and others. General Fusion is one of the most advanced companies in the space and is on track to deploy its first commercial plant by 2030. Helion Energy. This US-based company is also working on magnetized target fusion technology. However, their approach is slightly different as they use a rotating magnetic field to contain and compress the plasma. Helion has raised over $40 million in funding to date and is led by veteran aerospace engineer Jim Kurovala. The company is aiming to have a prototype ready by 2020 and a commercial plant up and running by 2025. Tri-Alpha Energy. This U.S. company is taking a different approach to nuclear fusion known as inertial electrostatic confinement, IEC. This uses strong electric fields to confine and heat plasma, causing fusion reactions to take place. To date, Tri-Alpha has raised more than $500 million from investors such as Paul Allen and Goldman Sachs. The company has made significant progress in recent years and expects to have a working prototype within 5 years. Lockheed Martin, one of the world's largest defense contractors, Lockheed Martin, is also working on nuclear fusion. The company is developing a compact fusion reactor that could fit inside a truck and provide enough power for 80,000 homes. Lockheed claims that their reactor could be operational within 10 years if they can secure sufficient funding. Given the company's size and resources, this seems like a realistic goal.